Dear students, I welcome you to this lecture on queuing theory. For example, you went to a hospital to take treatment from the doctor, and there are so many patients are waiting for the service, and you will be in the queue. So, queuing theory deals about the queue which you are standing. So, generally, you don't want to stand for much time. Even management also don't want you to make you to stand. So if you are a manager of a company where many people are getting service from the company, you don't want your customers to be waiting. So if you want to reduce the waiting time of a customer in the company for the service, you need to recruit more people who can serve it. But when to recruit the people for giving the service, or if the number of people are more, when to terminate them from the service such that the optimum utilization of the services will be there. So that is what the queuing theory tells about. So the objective of this queuing theory in this video is analyze and optimize the queues to improve system performance by minimizing waiting time, reducing overcrowding, managing resources efficiently, and enhancing customer satisfaction. Let us try to understand the basic terminology. For example, you went to a hospital for getting treatment, and the hospital is called as a system in operations research. In the system, so many patients are waiting in a queue. So that is nothing but the queue. The number of patients are waiting in the line are called as a queue. And once doctor call you for the giving service or treatment, so then you will be meeting the doctor and you will get a service from the doctor. So that is called as a service facility. So the total, the time which you are spending in the queue as well as service is called the time you spend in the system. So here we can understand one thing: the the rate of arrival of patients, that is called as the arrival rate lambda, and the patients who are waiting in the system are called as the queue, and the patients who are taking the treatment are called as utilizing the services, and the total hospital is called as the system. And once after you get the service or the treatment from the hospital, then you will be going away from the hospital, that is called as a departure rate. So the here arrival rate is nothing but the rate of arrival or the number of customers are coming to hospital per unit time, that may be per hour. So that is called as arrival time. And departure rate is nothing but the number of customers are going out from the hospital for unit time or maybe per hour is called as a departure rate. And queuing length here, if you observe in this PPT, and the system is nothing but the hospital, the length of the system is nothing but the length of the queue plus the service length of the service. So here the length of the queue is called as a LQ, so and the length of the system is called as LS, and the patients who are waiting in the queue is called as a WQ, and the patients who are waiting in the system, that means the queue as well as service, is called as the waiting time in the system. And the departure rate we already saw. And here in the service there may be a several servers, that means for several doctors are treating the patients. So server 1, server 2 and server 3, so these are called as the service facilities. And now if you see one important the thing, that is utilization factor, that is equal to the delta lambda by mu, that should be always less. If suppose the arrival rate is less than the mu, then only the utilization factor will be less than 1, then only there won't be much queue. If the arrival rate is more than the departure rate, this queue will never the end, so it will be always there will be a queue. So that is why utilization factor should be always it should be less. That means you need to provide a service which should be more than the arrival. So that is what the utilization factor tells about. The basic terminology whatever we are discussing here, let us see what are its meaning. The first one is arrival rate. The average number of customers arrived per unit time is called as arrival rate. Departure rate, average number of customers got service per unit time is called as a departure rate. Utilization factor, that is let us say rho, the lambda by the mu, that is a fraction of time service is busy. So that is the utilization factor. And the length of the queue, LQ, is the expected number of customers in the queue, and the length of the system, LS, is the expected number of customers in the system, that is in a queue plus service. And the waiting time in the queue is the WQ, the time and customer spends in waiting is called the waiting time in a queue, and the total time in the system is the time spent in a queue and service is called as the total time in the system. And let us directly discuss about the queuing models. There are several queuing models which we will be using in the queuing, and that queuing models can be represented as A slash B slash C and colon D slash E slash F, where A is the arrivals distribution, B is the departure distribution, C is the number of parallel services, and Q is the queue discipline, and E maximum number, that may be the finite or infinite allowed in the system, and F is the size of the calling source, that may be finite or infinite. And let us first discuss about the first model, model 1, MM1 and infinite. So it means many people are arriving, and many people are getting the service, and there is only one the server which is one, and calling people are infinite. So these are the formulas used in this model 1, and the average number of arrival per unit time is lambda, and the average number of departure per unit time is mu, and utilization factor rho is equal to the delta by mu, lambda by mu. Ideal time of system is equal to P naught is equal to 1 minus rho. So utilization factor is rho, so that is what you are utilizing. So ideal time of the system will be 1 minus rho. So then the probability of n customers in the system, that is let us say the Pn, that is equal to the rho power n into P naught, and the length of the system is equal to rho by 1 minus rho, and the length of the queue, LQ, is equal to rho square by 1 minus rho, and the average time waiting in the system is called as WS is equal to 1 by mu minus lambda, and the average time waiting in a queue, WQ, is equal to rho by mu minus lambda. Let us solve one problem based on this the model 1. A TV repair man, time taken to repair a set follows an exponential distribution with a mean of 30 minutes. Sets arrive for repair in a Poisson distribution at an average rate of 5 sets per 4 hours work day. So the technician repairs the sets in the order they arrive, first come first serve. Determine the following: what is the expected ideal time of the repair technician each day, and on an average how many jobs are in the system. So these are the things we need to find out. So any problem whenever they give, the first thing we need to see the arrival rate and then the departure rate. If these two are, if you know, and remaining all things we can able to find, that may be a length of the queue or length of the system, waiting time in the system or waiting time in the queue, these all things can be easily find once after you find out the arrival rate and the departure rate. Now let us carefully listen or carefully read this problem. So here the TV repairsman time taken to repair a set follows an exponential distribution with a mean of 30 minutes. That means this is 30 minutes he is taking to repair one set of TV. So that means these are the service he is doing. So service is nothing but the departure departure rate. And then he also said the sets arrives. That means the arrival time is 5 sets per 4 hours. So that is the arrival rate. So if you know these two, then the remaining things can be easily find out. So first of all, we need to see the time taken to repair a set is a mean of 30 minutes. So that means, and the sets arrive for a repair at an average rate of 5 sets per 4-hour work day. So from these two, we can understand that the first thing is the repair is nothing but the service he is doing. The average number of arrivals per unit time, that is lambda is equal to 5 sets for 4 hours. That becomes 5 by 4 sets per hour. And at the time taken to give service, it is that is equal to the mu, that is equal to 30 minutes for one the sets to be get repaired. So here sets per hour is given, so 1 divided by 30, and this is in minutes. So if you want to convert it, should be multiply with 60, then the two sets he can able to repair per hour. So one set he will take only 30 minutes. So in 1 hour he can able to repair two sets. So now you got lambda and mu. So then he is asking about the ideal time. So before that we will first see what is the utilization factor. The rho is equal to the lambda by mu, that is equal to 5 by 4 by 2, that is equal to 0.625. That is the utilization factor. And then ideal time of the system is P naught, that is equal to 1 minus rho, that will be 0.375 is the ideal time of the system. Then he also asked about the length of the system. The length of the system Ls is equal to rho by 1 minus rho. You already know rho, that is 0.625. If you substitute 0.625, you will get the length of the system. And let us go to the next problem. A arrival rate of a customer at a bank counter follows Poisson distribution with a mean of 40 per hour. The service rate of the customer clerk also follows Poisson distribution with a mean of 60 per hour. So what is the probability of 0 customers in the system? What is the probability of having 5 customers in the system? And what is the probability of having 10 customers in the system? Find LS, LQ, WS, WQ. So here the problem asked directly. So they given arrival time directly and as well as service rate also directly, and he is asking to find out the probability of having 0 customers, 5 customers and 10 customers in the system, and also ask you to find out length of the system and the length of a queue and waiting time in the system and waiting time in the queue. So here this is the direct question. Let us first try to understand the problem. And arrival rate he is given as, arrival rate is a mean of 45 per hour. So that means lambda is equal to 45 per hour, and the service rate is in the mean of 60 per hour, that is mu is equal to 60 per hour. Now the utilization factor rho is equal to lambda by mu, that is 45 by 60, that is equal to 0.75. Now the probability of n customers in the system, we know the formula here, that is Pn is equal to rho power n into P naught. P naught already we know, so we need to find out the P naught. P naught is nothing but the ideal time of a system. Ideal time of a system, P naught is equal to 1 minus rho, that is equal to 1 minus 0.7, that is equal to 0.25. Then the probability of 0 customers in the system, that is equal to P naught, that is equal to P power n into P naught, that is equal to P power n means n is a 0. So rho power n is not, it becomes a 1 and it becomes a P naught. So that will be 0.25. And the probability of 5 customers in the system, that is equal to the row power n. The row is 0.75, power n is a 5 into 0.25. That will be equal to 0.05. And the probability of 10 customers in the system, that is equal to 0.75 power n into 0.25. So you got the answer here. So that is how we need to directly substitute the value. And then we need to find out the length of the system, that is ls is equal to row by 1 minus row. If you substitute row value as 0.75 by 1 minus 0.75, it will become 3. That means the length of the system is only 3. And the length of the queue is the row square by 1 minus row, that is equal to 0.75 square by 1 minus 0.75, that is equal to 2.25. And the average time waiting in the system, that is ws is equal to 1 by mu minus lambda, that is equal to 1 by 60 minus 45, that is equal to 0.067 hours. And the average time waiting in the queue, that is equal to wq, that is equal to row by 1 minus lambda, that is equal to 0.75 by 60 minus 45, that becomes 0.05. So this problem is a direct substitution, and only thing is we need to find out the lambda and mu, then substitute in the equations. We need to remember all these equations, only then we can able to find the solution. Let us see the third problem. A vehicle passes through a toll gate at a rate of 90 per hour. The average time to pass through the gate is 36 seconds. The arrival rate and service rate follows Poisson distribution. There is a complaint that the vehicles wait for a long time. The authorities are willing to install one more gate to reduce the average time to pass through the toll gate to 30 seconds if the ideal time of the toll gate is less than 10% and the average queue length at gate is more than 5 vehicles. Check whether the installation of the second gate is justified. So here, if you properly understand the problem, here there is a toll gate, and for toll gate the arrival rate of vehicles are 90 vehicles per hour, and each vehicle is taking 36 seconds to get service, and arrival rate and service rate are following the Poisson ratio. And now here the service, everything is good, but there is a complaint that vehicles are waiting for long time, so the authorities are willing to install the another toll gate. So if they install another toll gate, what will happen? The vehicles will take only 30 seconds to get to get service. So at that time there may be an ideal time of the toll gate, and if the ideal time of toll gate is less than 10 percentage, and so no, it becomes a less than 10 percentage, and the average queue length at the gate is more than 5 vehicles, then check whether the installation of the second gate is justified. So here we need to first understand the problem. So whether already existing gates are sufficient, or whether we need to install one more gate such that the vehicles will not the wait in the queue. So let us try to understand, and the one by one. First we will try to understand and solve the problem for first current position. So current position, the vehicles are coming, 90 vehicles are coming per hour, and each vehicle is taking 36 seconds. Let us solve how many vehicles are waiting in the queue and what is the length of a queue, etc. Then now, and arrival rate of the vehicle per hour is 90 vehicles per hour. So 90 V means vehicles per hour, and service rate to pass the gate is equal to mu, that is equal to 36 seconds it is taking. 36 seconds it is taking per vehicle, but we actually required vehicle per hour, so we need to divide it 360, that means the seconds, this is in seconds, no, 60 into 60 divided by 36 seconds. So that becomes 100 vehicles per hour. So one vehicle is taking 36 seconds to pass through, and in that the rate, if the vehicles are passing, then in hour 100 vehicles will pass through the gate. Okay, so that means 100 vehicles per hour. So that is nothing but 60 into 60 by 36. That becomes 100 vehicles. Now let us find the utilization factor. That is rho, that is equal to lambda by mu, that is equal to 90 by 100. That becomes 0.9. So utilization factor is 90%, 90%. And the waiting number of vehicles waiting in the queue. Let us calculate LQ. So LQ is equal to rho square by 1 minus rho, that is equal to 0.9 square by 1 minus 0.9, that is equal to 8.1. That means the average number of vehicles waiting in the queue is 8 vehicles are waiting in the queue. And if one more gate is installed, revised time taken to pass the gate is 30 seconds. Now this is the way 8 vehicles are the waiting in the queue on an average, but let us calculate by taking the revised timing. So now let us assume that in the B case one more gate is installed. If one more gate is installed, the revised time to take to pass the gate is 30 seconds. So that means the service rate is increased because of installation of one more gate. So that is the 30 seconds. Now how many vehicles will pass through the gate if this service rate? So now let us calculate the service rate to pass the gate. Mu is equal to 30 seconds per vehicle, that is equal to 3600 by 30, 120 vehicles per hour. Because of the installation of one more gate, now the service rate is increased, that is 120 vehicles can be served in 1 hour. So now let us calculate the utilization factor, that is rho is equal to the lambda by mu, that is equal to 90 by 120, that is equal to 0.75. So utilization factor earlier is 0.9, but now because of one more the gate, the utilization factor came to 0.75. Now if one more gate is installed, the revised time is this much, and the service rate to pass the gate is 120, and utilization factor is this, and the average ideal time of the vehicles is equal to 1 minus rho, that is equal to 0.25. That means 25% of time the gates are idle, so facilities are idle. So now this is not acceptable, because they also only said only 10% of the ideal time is acceptable, but it is only 25%. So first of all, it is not acceptable. And let us also calculate how many vehicles will be waiting if suppose if we install one more the gate. So then the number of vehicles waiting in the queue, LQ, is equal to, with the revised utilization factor, that is equal to 0.75 by 1 minus 0.75, that is equal to 2.25 vehicles. That means the number of vehicles waiting in the queue is less than 5. So that means it is only 2.25, so that is very less. So because of this queuing length also, we can't accept that one more gate is the necessary to install. So finally what we can say, the number of vehicles waiting is less than 5 and ideal time is more than the 10%, hence installation of another gate is not justified. So that is the solution. Let us try to solve one more problem similar to this. And arrival rate at a telephone booth are considered to be following Poisson's law of distribution, with an average time of 10 minutes between one arrival and the next arrival. The length of the phone call is assumed to be distributed exponentially with a mean of 3 minutes. What is the probability that a person arriving at the booth will have to wait, and what is the average length of a queue? And the telephone department will install second gate when convinced that an arrival would expected to wait at least 3 minutes for the service, and how much must the flow of arrival be increased in order to justify the booth. So this is also similar to earlier, but it is around the telephone call. In a customer service or something, telephone calls they are receiving 10 minutes. Every 10 minutes they are getting calls, and once the call is come, and 3 minutes they need to give answer to those calls. So that is how they are actually serving. So now let us try to calculate the what is the arrival and the service time. So arrival rate of a call at a telephone booth is equal to 10 minutes per call. That is equal to 10 minutes it is taking per call. So that is equal to the 10 divided by 60 divided by 10. So that is equal to 6 calls per hour. So one call is taking 10 minutes. So total hour 60 minutes are there. 60 by 10, that is 6 calls they are getting per hour. So that is nothing but the lambda. And service rate per call mu is equal to 3 minutes per call. So they are taking 3 minutes for one call. That is equal to the 60 by 3, that is equal to 20 calls per hour. So finally they need to they can able to do service for 20 calls per hour, but only 6 calls they are getting per hour. And utilization factor is equal to rho, that is equal to the lambda by mu, that is 6 by 20, that is equal to 0.6. So now what we need to find out, that the probability that the person arriving at the booth will have to wait. So if he need to wait, how much time he need to wait at the booth? If any person who is coming to booth have to wait when there is somebody in the queue, that is equal to 0.3. He need not wait when there is nobody in the queue, that is the queue is empty, that is 0.7. Hence the probability of that an arrival does not wait is equal to 30%, and the average length of the queue is equal to rho square by 1 minus rho, that is equal to rho already we know 30, 0.3, 0.3 square by 1 minus 0.3, that is equal to 0.128 is the average length of the queue. And arrival rate of call at a telephone booth is equal to this all over. So now let us see the third C, that is equal to the telephone department will install a second booth when convinced that an arrival would be expected to wait at least 3 minutes for the phone. If it is expected for 3 minutes for the phone call, then they will be convinced and they will be installing one more the booth. So average waiting time in the queue will be 3 minutes, that is equal to rho by mu minus lambda. But here let us consider the service rate is same, that is equal to mu is equal to 3 minutes per call, that is equal to they can only serve 20 calls per hour. So that is same, but only thing is arrival rate, at what arrival the queue, the average waiting time in the queue will be 3 minutes. That is what the question. So that is why rho by mu minus lambda is equal to 3. So that is equal to, now mu already we are taking, that is as a 20 calls per hour, and mu already know, but lambda we need to find out lambda for wq is equal to 3 minutes. So that means rho by mu minus lambda, that is equal to rho is nothing but lambda by mu. So this is the old one actually. So now we are assuming that the mu is same and lambda is changing. So lambda by mu is 20 divided by 20 minus lambda, that is equal to 3 minutes. 3 minutes means 3 by 60. So because these are all in hours, so we need to convert this also into hours. So therefore if you solve this equation, then 60 into lambda is equal to 3 into 20, 60 into 20 minus lambda, that will be lambda is equal to 10. That means To justify the second booth, not both, the booth, 10 arrivals or calls per hour is required. So if they get 10 calls per hour, then there is a justification for installing one more second booth, otherwise not required. That's what the problem solution says. So let us solve one more final problem. So in a departmental store, one cashier is there to serve the customer, and the customer pick up their needs by themselves. The arrival rate is 9 customers for 5 minutes, and the cashier can serve 10 customers in 5 minutes. Assuming Poisson arrival rate and exponential distribution for service rate, find the average number of customers in the system, average number of customers in the queue, or the average the queue length, and the average time a customer spends in the system, and the average time a customer wait before being served. So these are the things we need to find out. So first of all, we need to see what is the arrival rate and what is the service rate. So if you see, the arrival rate is 9 customer per 5 minutes. So that means arrival rate is equal to 9 by 5 minutes, that is equal to 1.8. That is the arrival rate. And a cashier can serve 10 customers in 5 minutes. So the service rate is equal to mu is equal to 10 by 5, that is equal to 2. So then utilization factor rho is equal to delta by lambda by mu, that is equal to 1.8 by 2, that is equal to 0.9. And the average number of customers in the system, that is nothing but the length of the system, that is equal to rho by 1 minus rho. Rho we already know 90, and 90 0.9 by 1 minus 0.9, that is equal to 9. And B is average queue length, LQ, that also direct formula, rho square by 1 minus rho, that is equal to 0.9 by 1 minus 0.9, that is equal to 8.1. And average waiting time in the system is equal to WS, that is equal to 1 by mu minus lambda, that is equal to 1 by 2 minus 1.8, that is equal to 5. And the average waiting time in the queue is equal to WQ, that is equal to rho by mu minus lambda, that is equal to 0.9 by and 2.2 minus 1.8, that is equal to 4.5 minutes. So that is how we will solve this queuing theory problems. Thank you.